So let's review. So last time I gave my usual story that there were 3 sets of equations that we need to solve if we want to solve the embedding problem, which I'll use the colors. So this first is this relation between the h's, okay, which is called the Gauss relation. So that's an algebraic relation. Okay. Then we have the Gauss relation. Then we had this one, which is at the bottom, which were the Cauchy equations, if you can see, which relates, as I showed last time, partial differentiation across columns or rows. So you differentiate the ith column with respect to xj, differentiate the jth guy with respect to xi, and they're not equal, and the error term is this stuff, and the error term just denotes that there's some curvature in the system. If everything was flat, there wouldn't be anything to do, and it would just work out perfectly. And now I think Ricci is earlier, so let's see. Go back. I'm not sure if Ricci is further or later. And there's Ricci, so it's later. And Ricci was, again, partials, but it's not columns or rows because the A is not a, it's not a 2 tensor, it's not a mu j tensor. It's really just a scale, it's just vectors which are, you keep track of the vector by the nu and the mu. So it's just differentiating vectors, actually. Okay. And it again allows for, that this has to be solved. So we had to solve Gauss, Cauchy, and Ricci. And as I always repeat the same story, if that feels uncomfortable and you have some familiarity with fluid equations, it's like, this one is like the pressure term in Euler equation or Navier-Stokes. It goes along for the ride. Okay. Clearly, if you knew the h's, right, then you have an equation for the a's. Okay, there's no derivatives of h's there. So, and you can even write this in the fancy notation. Okay, so we have to solve Gauss, Cauchy, Ricci, but the equations look strange. This always bothered me because the equations look like curls in normal, I don't know what the Korean word for curl, maybe it's curl? Curl. Yeah. Okay, it looks like curl. Okay. So it's an unusual set of equations to solve curl somebody equals something. So it's not the usual sort of thing that we're used to doing in partial differential equations. So part of the issue is very simple-minded. How to rewrite them in a natural framework. Okay, so this just says, this slide says nothing more than if we can solve those equations, we've solved the problem. So if we solve the equation, but it doesn't tell us more than that. At least it's good to know. So and that's, I mentioned that last time, so that's a rough proof of what it means. And then I think I even did this last time. How many equations would there be in the case of surfaces? There'd just be 2 Cauchys, 2 equations, 1 algebraic condition. So now 2 PDEs, 1 algebraic is 3 equations. How many unknowns? And the answer is the 1, 1, the 1, 2, and the 2, 2, because the 1, 2 is symmetric. So 3 equations, 3 unknowns, and we're used to doing that stuff. Okay, so it looks like more or less a 2 by 2 conservation law, which in fact it is. It's not a conservation law because it's a right-hand side, but it really looks like gas dynamics or P system or whatever things people have seen quite a bit of. Okay, but things really change when you go up one more dimension, and then we have more for each component of the Riemann curvature tensor. There'll be a Gauss equation, so 6 Gauss equations. Let's continue. And these guys, when you start doing this guy with that guy and that guy with that guy, you get lots of Cauchy equations. In fact, I computed it here, so there would be 24 Cauchys, because there is one obvious double count, 6 Gauss, 9 Ricci, 39 equations. And how many unknowns? 18 H's, 9 A's, 27 unknowns. Most people would agree that 39 is not equal to 27. So something's wrong. And so what's wrong? And of course, that these have repetition. And that part is easy, that there's a repetition. The harder part is to know what repetition. And when I started on this stuff, I'll tell the story. One of the people who was explaining this to me was John Cleland, who works on the project from Colorado, and she wrote down for us all this stuff and said there has to be a lot of repetitions. But even she, who wrote a PhD thesis with a famous guy, Bryant, didn't know the repetitions. And then, as I said, as far as I can see, all the experts, when they write their papers, didn't know the repetitions. And so it seems that not so well known exactly what the repetitions are. Okay, I told you last time that in fact you can, it's not too hard to see the repetitions, and I give a sketch here. But the theorem, in fact, is due to Bloom, and I got it from Goner's paper on the web. So it's good to look at the web now and then. And he gives exactly the count. How many independent? He says, okay, in general, these are the number of independent ones, and the remainder of the Cauchys and all the Riccis are a consequence of, if you solve Gauss, I wouldn't have written it this way. I would have said, assume you've solved Gauss and then this, then all the other equations follow. So you don't have to solve them all, because if you solve some, you get the others for free. Just as in Navier-Stokes or Euler equations, if you solve the Euler equations, you get the pressure relationship for free, because it follows from the other ones by taking the divergence and using the incompressibility, if that helps you think about it. Okay, so I give the whole story here, and I mentioned it last time. So, in fact, and here I give a proof, if you're interested, of Bloom's paper is hard to read, but my proof is easy to read, more or less. Much easier than the Bloom. Okay, so definitely easier to read than Bloom. It's a direct computation. Okay, so I did it in, I don't know, 15 lines. So it's easier to read 15 lines than 15 pages. So, okay. Okay, so that's the story there. So this goes on, and how I did. So now let's get so now, as I said, let's go back. So I had to solve this Gauss, Cauchy, Ricci. Now we don't have to worry about Ricci. So solving Gauss and Cauchy, Ricci will take care of itself. But there's no free lunch, because even though if we've solved this one, which is Cauchy, we've solved Ricci. If we've solved the Gauss and we've solved this one, we've solved Ricci, but the A's still appear in the equation. So now in Navier-Stokes or Euler, we can somehow do a projection step to get rid of the P's, but it's not, here the projection step is not quite so simple. Okay, so one issue is we're going to have to, if we're going to close this system, we're going to have to get rid of these A's, because we want an equation just in H's. It's very rather logical. So how do we do it? Well, first, let's not worry about the A's. And the first thing is, as it says here, symmetrization. So how to write this nasty looking system, like this, curls, in terms of divergences. So I want to switch curls to divergences, because that's how I'm used to, nothing very sophisticated. That's how people in conservation laws, PDE people, we're usually used to doing things with divergences, because that's how the laws of mechanics are given. in terms of divergence. Divergence of somebody, whether it be the heat equation is divergence of the heat flux equals the heat production, the time-dependent part. So there's divergences. So I want to switch curls to divergences. So how do I do that? Okay. So first, can I use the board? It's very simple. Okay. Because so let's pick 3. When I say very simple, okay, since the students are here, if they understand my English, in the English the word is, there must be a correct similar Korean. The English word is sarcasm. So what's the Korean translation of sarcasm?
What, sarcasm?
Sarcasm. You know, you can look on your automatic translator.
Sarcasm?
Yeah, so what would be the Korean, is there a Korean word?
Kunja.
Kunja?
Kunja, okay.
Okay.
Because I'm being a little, I said it's easy. But that's not, I mean, it's easy, not really. So, okay. So it's easy. After thinking about it for 5 years, it seems easy. But when I first did it, it took, so.
Right?
Yeah, no, it's okay. It's only, okay. So really there's 2 pieces. The idea is, it's easier to see here than all this notation. Okay, so the first thing is pick up preferred x, x1, x2, x3. Pick any one of them you want, but just one, like x1. So we're going to treat x1 derivatives as being special. That means x1, roughly you could think of it as being time. So we're going to make it something like time. It's not a dynamic problem, but it helps. So think of x1 as being like the t in a system of partial differential equations. So that means I'm treating x1 special. So I'm going to take the x1 derivatives and treat them as special. So the equations which have x1 derivatives, I'm going to treat them as special. So this one, linking this one, is special because it says dx1 of this one is equal to x3 of this one plus an error term. This one is special. This one is special because it's the x1 of 3 is the x3 of x1. So those are special. But this, again, also, these are special because it's the x1 of h12 is the h2 derivative of 2 with respect to h1. So we have these special ones. Okay, how many special ones do we have? Well, you can immediately see the special ones. There would be from each row there is one pink one and one yellow one. So 2 special ones from each row. That means 6 special ones for each mu, and there are 3 mu's, so it's 6, right, times, right? So there's 1, 2, 6, right, times 3 because mu equals 4, 5, 6. So the 18 special ones. If you want to think of it, that's the time-like derivatives. But I haven't done them all, because I also have the non-special ones, which I'll do here. I didn't do this one and this one, right? So that'll give me a different bunch of equations. So I have 1, 2, 3. So I have non-special. So those are not dynamic. Those are static. Okay. Furthermore, if I had some divergence relation that related, say, the divergence of the row or going across here, a ddx1 here, a ddx2 there, a ddx, so that it added up for 0, then that would include this one. So if I take divergences across here, let's say I could take divergences. It would be for each row I'd get one divergence. So I'd get 1, 2, 3, okay? And there are 3, so if I had divergences, that would carry the non-special. So how many equations, if I could set it up in terms of special, which is the dynamic part, plus divergences, which is the static part, I'd have 9 plus 18, which is 27. So if there's no repetitions, okay, or no more repetitions than there should be, I haven't lost anything more, we know there are 21 independent caudacies. If I had done this, here I have 27. Okay, if I don't have more than 6, okay, that I haven't lost anything, then this encompasses all the caudacies. And this has the advantage that it looks like a dynamic problem plus a static problem. If you think of Navier-Stokes Euler, there's a dynamic part and a static part with the div equals 0. So it has the advantage of putting dynamics and statics. Okay, and why did I do that after thinking about it for a long time? Because when you write it this way, you can write the equations in the classical symmetric form of mechanics. And as far as I know, nobody noticed that before, but I don't know what people know. So that's the idea. So I hope that makes it clearer by showing it on the board. Otherwise, the notation is terrible, and but the idea is clear. So let's continue to the next one. Okay, so I show how you can do it. Okay, so all this notation will just make you sleepy after lunch and not very helpful. But, okay, one of the useful things, though, is introduce W. Okay, W is like an energy in the whole thing, and W is the sum of the determinants. So where is it? It was on the next one. Is it here? It should be either earlier or later. Where is W? I don't know. Let's try. Is W here? I don't know where W is. Should have been defined someplace. But so W is a scalar. It's just the sum of the determinants. Okay, so what's the point? Okay, so we have, here's the, remember I told you ones with special, one is taken out specially. That's the time-like ones. So here are the time-like ones. And then I multiplied by this Hessian of the W's. I'll explain why. Okay, and then there were the divergences, which I think is on the next one. Oh, let's so. No, the divergences were here. Here there's no special one taken out. We sum over all the derivatives. So it's a ddx1 plus a ddx2 plus a ddx3. So this is the divergences that I advertised, and this is the time-like ones. So I had taken the time-like ones and multiplied by this Hessian. Why did I multiply by the Hessian? Because there's a theorem of Lax and Friedrichs that says if you have a system of conservation laws, it's also Goodenough did it independently. I'll parenthetically remark that Goodenough was in Novosibirsk in Russia, Lax and Friedrichs were in New York. Lax and Friedrichs went on a trip to Russia. They met Goodenough. Lax and Friedrichs came back from the trip, and they published a very famous paper in the Proceedings of the National Academy of Sciences of the US. And the paper said if you have a system of conservation laws and you can find a so-called entropy, whatever that means, and you multiply by the Hessian, here W is the entropy, and you multiply by the Hessian, you make the system symmetric. So what does that have to do with anything? Then in 1980 something, I'm at a conference in France, and Goodenough speaks, and he says, number one, he did the result first. Number two, he told Lax and Friedrichs the result when they were in Russia. And number three, they were thieves. So not very nice. So a little, but Lax says he did not steal it. He doesn't remember such a thing, and they say they did it independently. So I believe Lax. Goodenough is a tough guy, so. But the idea was very convenient. So the ability to symmetrize that we learn from applied math, we can use in geometry. So an applied math idea turns out to be useful in geometry. Okay, so now it gets why. So what do the system of equations look like? Okay. It's rather lengthy, but I'll use the, okay. So it looks like a DD1, a D, and this now is summing over L. So okay. So a sum over all these L's. Okay, so it's DD1, DD, this has DD2, DD3 because the L is repeated here. So it has a system of equations. Here's a vector-like guy, and it's a DD1, DD2, DD3, and then a lower order term equals 0. Okay, and if you look at it, not very deep, okay, you see this guy is symmetric. So that coefficient is symmetric. And you see the transpose of this is this. Transpose of this is this. So the coefficient matrices are symmetric. It looks exactly as you would symmetrize the P system, the simplest 2x2 conservation law. Same idea works. So we've made the system symmetric. I write it down in all its gory details and show you that about the transposes and stuff. Now, if you were really a good geometer, which I'm not, or very good with indices, you could have done this without writing down all the mess. But I don't trust myself. I was always afraid I would make a mistake or nobody would believe me. So I wrote it down very carefully in the notes. So what does it say? So let's get to the story. We do all the thing. So it says, after all this work, okay, we started with Gauss, Codazzi, and Ricci, and I was able at least to take the Codazzi equations and write them in this form, where it's for each mu, not summing over mu, for each mu, so mu equals 4, 5, 6, for each mu, this is a set of equations that looks like symmetric DD1, symmetric DD2, symmetric DD3, this is summing over L, plus lower order term. But that's how the laws of mechanics are written. Okay? The only difference is if it was system of conservation laws, we'd have a use, if it was dynamic, we'd have, I won't write on the, we'd have du dt plus this equals 0. And this is how the laws of nature are written. Du dt plus this equals 0. I shouldn't say the mechanical laws of nature. Biology, I don't know. But mechanical laws, okay, du dt plus this. That's how mechanics looks. So I was able, after a lot of thinking, to write the equations this way. So this is Codazzi, but I still haven't used Gauss. And Gauss just says that you have all these, the U, capital U, which is the list of H's, and you can write the long list of H's into a smaller list of H's because it's an algebraic relation. You have, how many H's were there? There's, if you just count by symmetry, There's 6 here above the diagonal. So 1, 2, 3, 4, 5, 6 for each mu. So there are 18 H's and 6 Gauss relations. So you have 18 H's and 6 equations. So you can get rid of 6 H's if there's no degeneracy. So you can get rid of the 6 H's. It's like getting rid of some of the components here. And then we've reduced the number of unknowns. It's just using, as you normally do, you eliminate. It's like, it's in mechanics you say we're using the equation of state, or the constitutive relation. Okay. Okay, so here I did it for the linear case. It's not so important. I worked it out there, not important. Okay, now there's one trick which is rather really useful and very important. Okay. Remember there were 9 A's. But Dean Yang told me, we were having coffee in New York City. He walked over from his apartment. We met for breakfast on a Sunday morning in New York. And he said, you know that you can always set some of the A's equal to 0. I said, why is that? And he said, well, think of the pressure in a gas. If you change the pressure by a constant, say if it's a water wave problem, and you want to know what's the pressure on the water wave, people always set it equal to, pressure on the water wave equals 0. He said, of course you can do that because it doesn't make any difference. You can change it by a constant. So it's a convenient normalization to set the pressure equal to 0 on the water wave. So that's what I wrote here. Okay. So Dean said, it's a deeper thing, but the equations are not pinned down to Ricci equations. So you can pin them down to which pieces you want, that is by setting some artificial condition, and that means one thing you can do is set some of the A's equal to 0. So in this case, mu and nu go 4, 5, 6, so this is setting 3 of the A's equal to 0. Because there's a 4, 5, a 4, 6, no, that's it. So, right, 4, 5, 4, 6, and 5, 6. So there are 3 A's with the subscript 1 there. So you can set 3 A's equal to 0. If you do that, however, then the Ricci equations just become ODEs. It's actually integrals. It says if you know the H, then you know the other A's. You just integrate. So what does it say? Let's think about it from the point of view of functional analysis. Let's say I'm doing the computation and I got H to be an L2 function. If H is in even L1, but let's say, okay, H is an L2 function. If H is an L2 function, okay, that means when you integrate this guy over a domain, it's bounded by the L2 norm, plus the size of the domain. So if the domain gets smaller and you integrate, so here you integrate with respect to x1, you integrate with respect to x1, okay, you integrate, and you then integrate over the domain. It says nothing very deep, and I have the computation on the next page. It says the smaller the domain, the less these guys make any difference. So as the domain gets smaller and smaller, the contributions of the A's becomes more and more negligible. So even though they entered the equation, their influence is negligible. Of course, if you wanted to do a global embedding, you'd have to write this thing down as an integral and plug it in. That would make the equations integral differential equations, which as far as I know, no one has ever looked at, but yeah. So if you know the H's, you know the A's, just read them off. And you could plug them into the equation. So it truly is that this system is closed, because the A's enter, but they enter very modestly, harmlessly almost. Okay, how am I doing for time? We're doing okay. Okay, so let's continue. So that's linearization. Okay, this is proof that the A's are modest. Okay, anybody could have done that. I just put it in to make sure that's there. That's linearization. So here, let's do for the linearized. So it says, I said the U's, the unknown was a bunch of H's, and these are the special H's. So we can, remember there were all these. So there were 18 H's. But I eliminate 6 by the Gauss, so there are 12 H's left over, which I call H hats. And those are the ones that go in the equations. So we plug those in, and here I go through it. Okay, so it's not crucial, little linear algebra. And now we get a new system of equations, 12 equations in 12 unknowns for the H hats. So we had the Cadazzis, we plugged in the H's, we made use of Ricci by writing down those integrals, and now we have 12 equations in 12 unknowns. Okay, by multiplying from the left and the right, okay, I make the coefficients symmetric. So now this is truly classical. Here's for the linearized, maybe this is for the nonlinear case, I don't know. But, so it really looks classical. It's coefficient, symmetric coefficient matrix DD1, symmetric coefficient matrix DD2, symmetric coefficient matrix DD3. So it's really in pretty form. So I repeat myself, we started off with things that look like curls, and now I've changed it into things that look like divergences. And now I'm happy because I have more experience with divergences than with curls. And here are the coefficients. It's not crucial yet. Okay. So now, how could you prove an existence theorem? Well, that's the title of this lecture. Okay. So the simplest question, just to get started, is if you have an equation like this, with the left-hand side, I use this letter script L, that's the operator, and we want to solve the equation. So this is, say, if it was the linearized problem. You would say some linear operator on H, which was this divergences plus lower order terms, equals a given right-hand side. So we have a lot of experience with that. So what's the simplest one you can imagine? Everybody see this? So the first thing we do in a course in PDE, or one of the first, I don't know, is we say, how do you solve Poisson equation with u equals 0 on a boundary? Okay. So here's the Poisson equation, boundary, and let's give Dirichlet boundary condition. And how would we solve that? Well, the history of PDE is interesting if you think about it or look. So until the 1920s, or even further, in the 1920s, if you look in the ICM from the 1920s and you go to the PDE lectures, there'd be lecture of Cothiodori and the other famous people of the time, but Cothiodori's lecture I know for sure. So what did they know? Okay. They didn't know too much. Okay, they knew complex variables. So if you think that we're now 2013, right? This is 1920s even. Okay? The knowledge of PDE 100 years ago was really limited. Even though these problems of mechanics and geometry were well established, the PDE tools were very limited. So they knew complex variables. That means that they knew how to do things in 2 space dimensions. But clearly this is a problem in 3 space dimensions. So complex variable techniques won't work. And of course the complex variable techniques only work for elliptic problems anyways. Then the idea was they multiplied here, and then they wanted to know the variational. They said, well, let's change it to a variational problem and minimize that, maybe with a hair. I hope I have the sign right on there, so otherwise change the sign. Okay, and that was the so-called Dirichlet principle. So whether you could establish Dirichlet's principle that this thing had a minimizer, and we would call that minimizer the solution. And you minimize over all some class of functions for which u equals 0. Again, so this was a deep problem, and Courant himself established there, wrote a book called Dirichlet Principle. Okay, so again, 1920s in Germany, Courant is doing this. Okay, but first of all, that requires the problem has to be variational, and then stays linear. So then the people started to generalize the calculus of variations, and that was one approach. Okay. But to go back to the equation, what we see is how did things progress, okay? And this shows you how, in my view, how new the subject is. Even though we teach this to the students, usually, Laplacian u equals f. What do we say to the students? Okay, I think I'll do it here. We take the equation, multiply both sides by u, integrate over the domain, integrate by parts using the divergence theorem so that the boundary goes out. Okay. So it looks like this. Okay. So now this looks like inner product u with u, but not in L2, but some in this derivative norm. Let's put a 1 here, equals u f in L2. Okay. Now we've changed it into a very rather functional analytic setting that says, given as you run over all u's, as you for a fixed f, okay, can you find the u that satisfies this relation? Okay, so can you find the u that satisfies this relation? And the idea, okay, of putting in this functional analytic setting, as far as I know, was first given by Shmuel Agmon, and it's in his Rice lecture notes from the early 1950s, okay, which is just an application of the Rice representation theorem, which was then generalized by Peter Lax and Milgram to a more general case. So how do we do this? Well, we need a Poincare inequality, and Poincare inequality allows application of the Rice representation theorem. The amazing thing, I think, from the point of view of history, is how recent, which has become the fundamental tool that everybody would think of in the year 2013, isn't that old. It doesn't go back to Newton or Hilbert, Poincare. Okay. The idea of using functional analysis to get an existence theorem, okay, is comparatively new. And now, how can I tell? What's my proof of? How can I define what's new? So, what's my definition of new? And my definition of new is if we take the intersection of Agmon's life and Slemrod's life, the two intersect to the point that I gave Agmon a ride in my car a few weeks ago. So, and he wanted to know what I was working on. So the point is that, okay, these ideas are somehow profound and useful. So what makes this work, of course, is the Poincare inequality. So we need some way that when we take, if we call this L or minus L, then we multiply this, so let's call this L, okay? Let's call it, minus L, that we need minus L, which would be minus Laplacian, to have the good estimate. So the Poincare inequality for minus u would give some constant times u squared and L2. So we need what's called coercivity. Well, same proof would work here. I wrote it in this form, so it's nothing very deep. Okay, you first define weak solution, but it all comes down to you multiply by h, take the inner product, and if this guy is coercive, that it satisfies the Poincare-like inequality, you have existence. And that would be the way you'd have to do. So there'd be two steps. Okay, first prove this result, that coercivity works. That's not hard. And then check it in an example. So far, so good? Okay, so now unfortunately, or fortunately or unfortunately, coercivity doesn't work. Okay. So why doesn't it work? Let's do I have the thing here. Let's do the example here. So let's do it with respect to the Poisson equation. So let's write it, I'll write it minus. Okay. And I'll put it in a B now. So for Poisson equation, I said, we'd multiply by u. Let's pretend it's a B here. And then we'd integrate by parts, and we get grad u squared plus bu squared, and then we get here fu. So for this one, if b is positive, we're happy. If b is equal to 0, we're happy, because we still can use Poincare. That is, it's greater than some constant times u squared. But unfortunately, in the one I have, when this is not Laplacian, but this L, there is no Poincare. Okay? There is no Poincare. On the other hand, there is a B. So what saves you is not this guy, but the B. You have an inequality, okay? Not that LUL is equivalent to the H1 norm, which is the one we have here, and then we use Poincare. It's that LUL is equivalent to the L2 norm, because this is the... So we just use the... So it's not the same, and that makes sense because it's not an elliptic system. So we can't expect higher derivatives. So, but that's the idea. It's following the usual ideas of the first day of doing anything on elliptic equations, multiplying and integrating by parts, but there is no Poincare in it. You don't get grad u squared. You don't get equivalence to H1, you get equivalence to L2. Anyways, that's roughly, and it's worked out here. Here, I show you that this is what makes it work. That the L, even though it's a differential operator, it's d dx1, d dx2. Okay? This thing we'll have to check is not that it's coercive on H1, but that it's coercive on L2. Okay. And there's some functional analysis. Why did I do this? And the answer is, I worked it out because I thought when writing the notes, okay, why refer to too many books? It's easier to work out the proof. It's not a hard proof, so it could be a homework exercise, so I worked it out. Okay. Okay, so there's the theorem. And now we get to the moment of truth. Okay, because so far it's just fooling around and I have 20 minutes or so. So what we did was, it works in the linear case, it works in the nonlinear case as well. Okay, it says if you can prove coercivity of this divergence guy, okay, then you solve the linear problem for the linear case. And in fact, for the nonlinear case, how would you do it? And the answer is you just iterate successive approximations and use contraction mapping principle. That would be if you could do such a proof. So how do we state this with respect to the original system? It says here was the system. Okay, where was the system? Oh yeah, let's go back. Do we have the system? No. So let me go back on instant replay. Where was the system? Okay, sorry. I wanted the system with the H's. Oh, I had it, sorry. Here. So we have to check coercivity. Can I use my finger as opposed to writing? So let's imagine. I want to solve this just like Laplacian U equals F. What would you do? You'd multiply by H and integrate by parts. Right? So what happens when you integrate by parts? Well, you'll get, of course, you'll get an ddt of h a0. When you integrate multiply by h, you'll get what terms? Let's just. Ooh. It's very simple. So again, I promise. Where was the? Yeah. Same idea as here. Let's just do the first term. Let's just look at it. So it's dd, right? Like that. Plus, so what would you do? If you didn't know anything, you'd multiply by h. Then what would you do? Let's not worry about, just treat it as ddx1. So what would you do? You'd say this is ddx1 of h a0 h with 1/2, right? Why is that? Because ddh1, you'll get a ddh1 a0h plus, let's not worry, plus another ddh1 h hat a0. Now why are those two add up to the one with the a0? Is because a0 is symmetric. So if a0 wasn't symmetric, all bets are off. Hence I worked so hard to make them symmetric. How hard? 5 years. Okay. So now I got it. But there's an error term. Okay, this is dd. And then we have also minus 1/2 h dd1 a0 h. So this one, okay, let's just look at the first term because they're all the same. So you have, we took the equation, say the first term in the equation, you multiply by h. You write it this way. You integrate over the domain. You rig up the boundary conditions. Well, the easiest way would be when you integrate this one by the divergence theorem, okay, well, integration by plus. Okay, this one is the value upstairs minus the value downstairs, and if the boundary conditions is 0, it's 0. If the boundary conditions, you want to do it a little different, you just have to make sure you get the right sign, that the boundary conditions at the top minus the boundary conditions at the bottom give you an inequality. And this was first done by Friedrichs himself. Friedrichs was a smart guy, and I think the year 1960 something. So Friedrichs defined the subject of positive linear operators. Why did Friedrichs work on this? Because when you write down, do this trick, it didn't make any difference whether the equations were elliptic, hyperbolic, mixed. So Friedrich was interested in a general theory for mixed hyperbolic elliptic problems. So Friedrich's, like me, of course, knew that the very interesting problems were exactly when the case A was symmetric, but the equations were of no particular type. Okay, so you've multiplied, you've set it up this way, you integrate it, but now you have this term. So you can't get anything from this term, so it says all the information is not from the A's, but from the derivatives of the A's. So all the information is from the derivatives of the coefficient matrix. This is a quadratic form where the coefficient matrix is not the original coefficient matrix, but the derivatives. So when you do this for each term, you need positive definiteness in the derivatives of the coefficient matrices. Okay, now the idea was done something like this. Again, in the case of n equal to 2 space dimensions, by Chin Han and Hung in their book generalizing a work of C.S. Lin. C.S. Lin is in Taiwan. He did a famous thesis with Nirenberg at NYU exactly on this two-dimensional case. But C.S. Lin's proof is harder, and doing it this way is easier. What Han and Hung, as far as I know, and I spoke to Han, they didn't realize that the setup that they did in 2 dimensions works in any dimensions. Of course, it takes a lot of effort. My opinion is the setup where I did a set thing up here, the general case is easier to see than the mess they have for the special case. Okay, so now we go back to why is that theorem the way it is. Okay, and then so here it is. So the positive definiteness is in the derivatives of the coefficient matrices. So the theorem for this linear problem says if the quadratic form is positive or negative definite, doesn't make any difference. Because you'll get some inequality either way. Okay. Then there exists a unique weak solution to the linearized embedding problem. So I've changed the embedding problem to an algebraic problem. But now I have the conclusion. Okay, that's about the end of the notes, I think. And I thank everybody, including everybody here, if you want to see. Guys. So, but I'll shut off the projector and now say this is only the beginning of the story. Of course, I'll stop in a few minutes, but can we erase it? I'll use the blackboard underneath, so I won't use this. Shut off the computer. And say, if I had stopped here, nobody would publish such a paper. Because what good is a theorem without example? So it says something like dd1 of a0, I don't know how I had it. Okay. Plus dd2 of a1, I don't know, something like that. Let's just do how many coefficient matrices. But it's dd1 maybe of a1, and I think the dd2 of a2, dd3. I repeat the time one twice. So, but it's derivatives of coefficient matrices plus some lower order term, and we wanted this guy to be positive definite. But how do you know if you can do that or not? It's might be a vacuous theorem, a vacuous statement. So how can you check such a thing? So how to verify such a thing? So we have to find some place, some example where we can understand how to do this. Well, when we do let's think of the linearized problem. For the linearized problem, you give me some fixed h and we linearize about it and we try to see what's going on. So in the linearized problem, you have some fixed guy that you linearized about, and I'll call that, call it h. So these a's depend on the h's. So now you're searching for some set of data that you gave to the problem, okay? And you're going to hope that you'll find some set of data which makes this positive or doesn't equally the same, negative definite. And I didn't know how to do this, okay? Because what it's really a search problem. You're going to let somehow the computer, whoever the computer, run over all the infinite possibilities of h. And can you find some h for which this works? But things were lucky, okay? So I typed in, I know this is called, when you write it as a quadratic form, okay, this is asking that the quadratic form be positive or negative definite. In math, and in Word and English, it's called pencils of quadratic forms. Because it's nothing more than taking linear combinations of quadratic forms. Because if I run over all h's, and here the h's actually occur so that these become, this guy occurs linearly in the h. So it becomes linear combinations of guys. So this guy just becomes, I'll use different letters. Can I use capital A like that? So it becomes linear combinations of matrices. So when you ask, is a linear combination of matrices, okay, if you put in the h's, it would be linear combination of quadratic forms. Okay, so this would be transpose. So, and I knew about linear pencils of quadratic forms from when I was a graduate student doing Lyapunov functions. I knew the word, and I knew that in Gottmacher's book, which is quite a famous book, Gottmacher was a Russian mathematician, he had a discussion of pencils of quadratic forms. And it's also in Mirsky's book, which is also very old, that I had used as an undergraduate book called Theory of Matrices. So I, of course, went and looked in Gottmacher's book. I looked in my own copy of Mirsky's, hoping I would find something that would tell me when this linear pencil of quadratic forms can be made positive definite. I did some hunting on the web, and at first I didn't find anything. But then I typed it in, and there's some place called Math Exchange where people ask questions and then other people try to answer them. So I typed it in on the web, on Google search, and I found this Math Exchange called Math Stack or something. It's worth trying. And then somebody had asked the question, said, I'm doing some problem in theoretical physics, and I need to know when I can make a linear pencil of quadratic forms positive definite. And the person replied, he said, oh, you should read Lovash's notes. Now Lovash is, okay, and I forgot his first name, but so Lovash is younger than me, not too much. So Lovash is he was head of the IMU. So now the current head is Ingrid Dobeshies. I think he was after John Ball, right after John Ball. Well, Lovash is a Hungarian mathematician. And Lovash gave a series of lectures at Microsoft Research. So if you type in Lovash is, if you type it on Google, Lovash notes, Microsoft research, you'll come up with the notes. They're there for free. Okay. Microsoft doesn't need the money. Okay. So he was at Microsoft as a visitor. I'm sure he got paid very well, and he gave these lectures on convex programming. So it's a thing that we're not used to using in applied math, or certainly not my branch of applied math. Okay. That operations research and linear programming is something you just don't use. But if you think about it, it is a programming problem because you're trying to run over all possible guys, all possible x's, to achieve some goal. But it's a linear in the sense that the x's appear linear. Okay, so Lovash there gives his, has some results exactly on this problem, and then he gives a reference, and as the guy did on the web, to somebody who actually had worked it out further. So Lovash's results, well, very neatly stated, were actually done in 1948 by a guy who, of course, I had never heard of. Something I have it there. I'll misspell it. Bowenblust, something like that. And he was in America. He was at Caltech, professor at Caltech in the math department, and he had done the same stuff. So this was really luck, because now I knew how to do the test. Okay. So what is the, and I wrote it down, but it'll take me time to write it down, but I'll just say a few words. So what does Lovash's test come down to? It says, it's like the Fredholm alternative. It says, take each one of these terms. So here, h hat okay? This is transpose. Then do it the 2-1. So what would if you're thinking Fredholm alternative, what would this Fredholm alternative? It would say, if the only solution to each set of equations is 0, so you have a bunch of equations, you set each one equal to 0. If the only solution is 0, then amazingly there's some set of x's that will make it positive definite. And they call that, again, since I'm not, they said this is a generalization of a famous, again, Hungarian mathematician, Waukesha's lemma, which again comes from convex analysis. So then I checked, okay, so when can I apply this result that Lovash states, which was really done by this guy, which really followed from this guy, not a subject we're used to doing, and I worked very hard to find a simple case and to see when it happens, and the answer is, what did it have to do with geometry? And remember, in the Riemann curvature tensor, in the case n equal to 3, there were precisely 6 R's. That is, if you wrote it as a Ricci tensor, there were 6 R's. And the theorem says, okay, so it's, what do you need to force, when these guys are equal to 0, to force that guy equal to 0? Well, usually that means somebody should not be 0, so that these don't become degenerate. So you need somebody not equal to 0 to force this equal to 0. So what's the not equal to 0? And the answer is one of the R's, at least one of the R's. So one of the components of the Gauss curvature. At least one. 2 is good, 3 is good, but certainly, okay, 1. If they're all 0 at the point, then the problem is still, in some sense, doable in the result, but it becomes more difficult. And this easy coercivity, if you lose the coercivity, and if you lose the coercivity, the problem becomes trickier. And that way, contraction mappings doesn't seem to work for the nonlinear problem, and you need Nash-Moser. And that's a bigger piece of machinery. So now to finish, because this is the last 5 minutes of my last lecture, perhaps forever at KAIST. So then, why was I happy with that result? And the answer is, it has to do with a local story. So why? Because in roughly 89, maybe earlier, 85, I can look it up. Okay. There was a paper in the Japanese of two Japanese, Nakamura and Maeda. So first it appeared in the Proceedings of Academy of Sciences of Japan, and then they published the full paper in the Transactions of the American Math Society. And what did they prove? They proved this result, but they used heavy Homonda machinery. Okay. So I was extremely pleased to see, as far as I can see, that you can produce their result without needing micro-local analysis and rather deep mathematics. So somehow, even if this mathematics looks deep, maybe to the person walking on the street, to the bus driver, it looks deep. But compared to that stuff, it's definitely not deep. Okay, so that's number one. Number two, it was very nice to meet Nakamura, who was here last Friday, sitting right there where you're sitting. And he said we had met before, but I didn't remember. So Nakamura was here and now lives probably in Incheon, and he's now at Inha. And last but not least, to finish up the talk, if my proof is not wrong, which I have, not only do I think Nakamura's result, and with Maeda, which I've now reproved using contraction maps, holds in the case of n equal to 3, as far as I can see, the same argument arbitrary n. So that's what I told Nakamura last Friday, which he was happy to hear. He'd like to see the proof, and I hope I can get a proof, finish up the paper this year. But I believe the Nakamura-Maeda result is true in any number of dimensions. So you're taking this n-dimensional Riemannian manifold and embedding it into n times n plus 1 over 2. So exactly to determine case, as many equations as unknowns. And as far as I can see, it's always true that if you have at least one element of the Riemann curvature tensor not equal to 0, you can always do a local embedding. Local, because it's contraction maps. To get the contraction constant less than 1, everything has to be, you have to make somebody small. So it's a local result. So it says roughly, you don't need C infinity. You need whatever the K is to make the usual Sobolev space stuff work. So I started this story, giving these lectures 3 years ago, at least. And now it's sort of reaching the end. And somehow it brings it up to the present day that Nakamura was sitting in that seat. And maybe, somebody else will want to continue even to harder problems. Okay, 3:12. Stop now. Good.